Welcome to Organic Chemistry with Crip. We continue our beginning steps into organic chemistry with a little bit of review of chemical structures from General Chem, as well as formal charge. And we introduce the concept of normal valence. And this will help us to make sense of degrees of unsaturation with given chemical formulas, and make sense of drawing possible constitutional isomers. Let's begin. So some variant of this would have been covered in general chemistry, and let's just cover this from the beginning. So good Lewis structure drawing always starts with some kind of formula and definitely counting total valence electrons. You will see that as we get into skeletal structures and such, we won't necessarily have to go step by step in this regard, but it's always an excellent way to check your work, counting total valence electrons. Notice the first thing that's formed was sigma bonds. Sigma bonds are our most attracted bonding molecular orbitals. And so you should have formed sigma bonds first, right? With them representing two electrons attracted to two nuclei, and then placing unshared pairs, typically completing the more electronegative atom first. And hopefully you had discussed and became comfortable with the concept of formal charge. And so you can see in our structure here for nitrate ion that the oxygen should be negatively charged because there are 7 electrons directly on the oxygen atom, whereas it should have 6 in terms of its valence electron capacity. And nitrogen, having only 3 bonds in this case, would only have 3 electrons directly on the nitrogen atom. And so because its valence electrons would be 5 valence electrons, we'd indicate a lack of electrons on that nitrogen with a 2+ charge. Now, it's typically good practice to place formal charges before you form the pi bonds, because pi bonds, right, can move in resonance structures. And so you can see the completed structure would have 3 resonance structures associated with it, and it would be good practice to flow from the negative charge to the positive charge. And so this would be, again, something very common that you had done in general chemistry, and we're just reviewing the basics here. Now, formal charge is your friend. Formal charge is super, super helpful for drawing structures very quickly, and it's also helpful for understanding reactivity. It's a way of keeping track of that electron density directly on the central atom. So if we look at our water molecule here, we've got 2 unshared pairs and 2 bonding pairs, but directly on that oxygen atom. So even though it's fulfilling the octet rule with 8 electrons total around it, directly on that oxygen atom, there are only 6 electrons. And so that's why oxygen in the water molecule is neutral. Hydroxide, however, right, in forming only 1 bond, there is much greater electron density. So there are 7 electrons on that oxygen atom versus 6. And so that's why we put a negative charge on that oxygen atom to indicate that there's 1 more electron located on that oxygen. Now, you should know intuitively, if we have greater electron density in one location, there will be greater amounts of repulsions. And therefore, those electrons are going to be less stable, less attracted to that nucleus. They're going to be more reactive. And so those unshared pairs associated with that negative charge, that's where the reactive site will begin in a reaction. Conversely, if we have less electron density, more bonds, we'd expect greater attraction. So if you're looking at hydronium ion to the left, we see oxygen. Again, all of these with oxygen fulfill the octet rule. That's not what's in question here. What's in question is how much electron density is on that central atom. And we can see there are only 5 electrons. 5 electrons located directly on the oxygen atom. We indicate that lack of electron density with a positive charge. What do you think that means for those bonds? Those bonds are even more attracted to that oxygen nucleus. You may encounter at times in certain textbooks this notion of formal charge is just bookkeeping. That is completely inaccurate. Formal charge is not just bookkeeping. Formal charge has a correlate to the real representation of what's going on in terms of attraction and in terms of electron density on that nucleus. So things do get a little bit subtle, but in terms of tracking electron density, this should be very, very simple and straightforward. So why is formal charge incredibly useful? In addition to making sense of reactivity and mechanisms, it's also incredibly useful for drawing excellent structures quickly. We introduce another concept, probably one that you haven't heard before, which is normal valence. Normal valence is not valence electrons. You know what valence electrons are. Carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7, etc. This is different. This is referring to the number of bonds that atom will make with a formal charge of 0, with it being neutrally charged. So hydrogen, of course, can only form 1 bond. Carbon can form 4 with it being neutral. Nitrogen will form 3, oxygen will form 2, and fluorine will form 1. This is very, very helpful when drawing structures quickly. And you can see that in terms of charge, the greater the electron density, so carbon, if it's neutrally charged, will form 4 bonds. Notice when it's negatively charged, right, we've got less bonds on it, right? So there are now 3 bonds, 1 unshared pair. Look at nitrogen. Nitrogen typically has 3 bonds, 1 unshared pair. And notice now when it has a negative charge, it has 2 bonds and 2 unshared pairs. A greater negative electron density, right? More electrons are directly around. Again, here, water, 2 bonds and 2 unshared pairs. But when it's in the state of hydroxide or any time that it's negatively charged, right? 3 unshared pairs, 1 bond. Notice the only thing that kind of sticks out as an outlier to this trend is on the opposite side with the carbocation. Notice we can't have a situation, right, where we have more than 4 bonds for carbon, because then that would break the octet rule. So you have a situation here, we have 3 bonds but no unshared pairs. And so that yields that carbocation, that carbon with a positive charge, because there's only 3 electrons directly located on it. Versus nitrogen, you can see more following this pattern. For neutral nitrogen, it was 3 bonds, 1 unshared pair. For the positively charged nitrogen, there's 4 bonds, right? No unshared pairs. And then for the hydronium ion indicated, right? It has 3 bonds, 1 unshared pair, versus water had 2 bonds and 2 unshared pairs. So again, this notion of normal valence directly connects to formal charge. And if you make that connection, then once we shift towards drawing Lewis structures, you're going to see a connection between these techniques. So keeping this in mind, that those simple elements in terms of normal valence, that hydrogen only forms 1 bond, that carbon forms 4 bond, right, when it's neutral, and nitrogen forms 3, oxygen forms 2, etc. If we look at different possible chemical structures, we can see something like a condensed formula at times. A condensed formula, notice how I'm writing out the condensed formula for this substance. I've got CH3, CH2 in parentheses with a subscript of 4 after it, and then CH3. Again, it's the idea that carbon will form 4 bonds. So when, and hydrogen must only form 1. So those 3 hydrogens that are being indicated, CH3, they must be bonded to that carbon preceding it. We could write H3C, but it would be equivalent to CH3. And so many times you'll see either. And then that parentheses is indicating multiple of those. So if carbon, if it's neutral, will form 4 bonds, we'd expect those 3 hydrogens to be bonded to that terminal carbon, and then that carbon also be bonded to the next carbon. And since that is being indicated in a chain, why? Because CH2, that's only 2 hydrogens bonded to each carbon. And so that means each carbon with those 2 hydrogens must be bonded to 2 other atoms. And in this case, 2 other carbons. So in the chain, each carbon is bonded to 2 hydrogens. And then finally at the end, the other terminal carbon, we've got 3 hydrogens bonded to them. So each carbon has 4 bonds, each hydrogen only 1. Notice our structural formula is illustrating this in terms of its structure. We can also represent it by a dashed wedged formula. Remember that if carbon is forming 4 bonds, it is sp3 hybridized, it is tetrahedral in shape. So if we were to draw this 3-dimensionally, they would definitely not be existing all in the same plane. Absolutely not. But based upon VSEPR theory, they would be pushing each other out to the most stable configuration. And what you see represented in the dashed wedged formula is how they would exist spatially. Of course, you will see in this course a lot of times a combination of a condensed formula and a structural formula, just because chemists sometimes are a little bit lazy. So notice I've got H3C and then the carbons being shown bonded. But the most frequent technique that we will use in organic chemistry is the skeletal formula or the bond line formula. And this simply hides the carbon atoms and the hydrogens attached to carbon atoms. So skeletal structures, again, hide carbon atoms and hide the hydrogens attached to carbon atoms. We show everything else. But again, this is why formal charge is so important, because you can see illustrated to the right that we have a couple of carbocations. And if you look carefully at the structure of the carbocations, if we indicate a positive charge on one of the carbon atoms, that is indicating a lack of electrons. So you can see at the top one, that carbon atom, that terminal carbon that has a positive charge, it only has 2 other hydrogens attached to it, versus the other carbon atom below it that has a positive charge, that carbocation, that is what we call a tertiary carbon, because it's attached to 3 other carbon atoms. And notice there are no hydrogens bonded to that carbon atom with a positive charge. And that completely connects to this notion of normal valence and formal charge, as well as the skeletal structures that we will draw tons of. Now, with all this in mind, we can shift to something that we call degrees of unsaturation. So again, one thing that I will stress in our organic chemistry course is connecting skills, techniques all together. The more you make connections between them, the more you establish their usefulness, the more you put them into your long-term memory. So degrees of unsaturation is really useful for thinking about different possible constitutional isomers, or just isomers generally. So let's revisit this notion of our skeletal structure, right? Since carbon has a normal valence of 4, we'd expect that every carbon atom is bonded to 4 other atoms. So the terminal carbons are the only carbons that would be bonded to 3 hydrogens, versus the carbon atoms within the chain would each be bonded to 2. Now, notice what happens if we form a ring structure. in forming a ring structure, we have now, you could think of it as bonding the terminal carbons together, but that would eliminate one hydrogen from one terminal carbon and another hydrogen from another terminal carbon. So it would eliminate two hydrogens. But there's also another way where we could eliminate two hydrogens, and that would be perhaps in the formation of a pi bond within the structure. So whenever we have a ring structure or we have the presence of a double bond, that is a pi bond, we would have what's called a degree of unsaturation, in which two hydrogen atoms would have to have been removed to either form the ring closure or the pi bond. And so notice in our benzene ring here, we've got a ring structure, but we also have 3 pi bonds. Altogether, that means we have a total of four degrees of unsaturation, right? There would actually have to be 8 hydrogens removed to go from hexane to benzene. Okay, so in order to calculate degrees of unsaturation from just looking at the chemical formula, we are taking the maximum number of hydrogens that we could possibly have, and we are subtracting it from the actual number of hydrogens in the structure, and then dividing by 2 to get the degrees of unsaturation. So again, carbon in the chain, inside the chain, not terminal carbons, but inside a chain, will always have 2 hydrogen atoms bonded to it. Nitrogen inside a chain will always have 1 hydrogen atom bonded to it. Each oxygen in a chain, right, because it only has 2 bonds, will have 0 hydrogens bonded to it. We treat halogens as equivalent to hydrogen. And then finally, the ends of the chain will have an additional 2 hydrogens. The terminal carbons have an additional 2 hydrogens, right? One on each side. So if we are given a chemical formula, right? If we're given C5H5N, just the formula. Now, the substance is being shown on the left, but if we just have C5H5N, the maximum number of hydrogens is the carbon, right? 5 times 2, 10. And then from nitrogen, we have 1 nitrogen. So 1 times 1, 1. So that's 10 plus 1, 12, 11 plus 2 from the terminal carbons, right? That's 13. That's 13, okay? So that's the maximum number of hydrogens that we can have. But the actual number of hydrogens in the formula, notice the formula says C5H5N, so C5H5. So we've calculated the maximum number of hydrogens from carbon and nitrogen, and now we are subtracting the actual, the H5. So 13 minus 5 is 8. 8 divided by 2 means that we have 4 degrees of unsaturation. So this would be one of the possible structures that we could draw, in which we'd have a ring. A ring would be 1 degree of unsaturation, and then 3 pi bonds, which would be an additional 3, so a total of 4 degrees of unsaturation. So let's take a look at how this might look in putting it to practice in drawing different possible structures. Here we've got C8H18, 8 carbon atoms here, right? 8 times 2 is 16, plus the 2 from the terminal, 18. We've got actually 18 hydrogen atoms in the formula. So 18 minus 18, of course, is 0. This has 0 degrees of unsaturation. And so notice we have so many different structures that are possible to draw with reference to this given formula. Honestly, the larger the formula in terms of carbon atoms, the more complicated this gets very quickly, because you can see any kind of different placement in the structure will yield a different substance. So in conclusion, we refer to this distinction of isomers as we're drawing these structures and thinking about degrees of freedom. We really, at this point, are only referring to constitutional isomers. Iso means same, mer means unit, and constitutional refers to that their placement their width placement or their structure is different. They have the same unit, same formula unit, but different structural arrangement. This is in contrast to stereoisomers, which will have the same structural arrangement, but different three-dimensional conformation in space. And so we can have mirror images that enantio mean in opposition to each other, versus the diastereoisomers are not mirror images, that dia meaning really that they are through and through not mirror images, however still having similarity in terms of their structure, not their three-dimensionality. So with this, again, we will be focusing on constitutional isomers at this juncture in class, and using that degrees of unsaturation to help us draw as many structures as possible. Till next time, Crip.